We're going to talk next about one of the concepts that people have a hard time imagining because it does some weird things to us when we really follow it through to its conclusion. But it's still kind of cool, so we're going to look at it and talk about it. And the concept is called vapor pressure. And what does vapor pressure mean? Well, let's consider a bowl of water sitting out. And if you wait long enough, like maybe 3-4 weeks, and you come back, what's going to be left in there? Absolutely nothing, right? That bowl is going to completely have evaporated and all the water is gone. Now, did that happen like boom, like once in the night when no one was looking, all the water went, whee, got all left? Or was it happening continually and gradually over time? And hopefully you come up with it was continual and gradual over time, not some little gremlins coming in and doing it late at night. And so what it means is at all times, there's a little bit of gas that's water vapor, right? If we're evaporating, we're turning the liquid into gas. And so there's a little bit of water gas coming off of that guy at all times. And if we had this cool little water pressure sensor here, right? Remember, pressure is force per area. So we just need something that the water could hit and we could detect its pressure. Then there'd be a pressure of that water gas right on top of that liquid that's fairly constant, right? Because that water gas is always just constantly, slowly evaporating. And we could measure the pressure of the water coming off of that liquid. And we'd have to distinguish that from the air around it, which has its own pressure, right, about 1 atmosphere. But if we could do that, then we'd be able to measure that. Now, that's what we call our vapor pressure, right? So measuring the pressure of the water vapor is our vapor pressure. Now, instead of cold water, let's take some really, really, really hot water. Really, really hot water is going to evaporate faster or slower. Hopefully you came up with it, it's going to evaporate faster, right? You boil water, it's going to evaporate really, really quickly. And so there's actually a lot more gas coming off than there would be in the cold water. So we have a lot more of these little squiggly lines. And if our little pressure sensor was measuring here, there'd be a lot more water hitting it. And so we'd have a higher vapor pressure here than we did in the first case. And so we see that vapor pressure is something that exists. It's constantly there above any liquid that's evaporating, but it also changes with temperature. The higher the temperature, the higher the vapor pressure. Does it change with size? The answer is no, it doesn't change with size because we're only measuring it, kind of technically in this one little spot. And so we moved over to a different spot, about the same stuff would be coming over that different spot, and about the same amount would come off that different spot. Now, the amount that comes off, absolutely dependent on size. If I have a little tiny bit of water, a little bit's going to come off. If I have an entire lake, a huge amount's coming off. But if you look at the pressure, which is the force divided by the area, right, taking into account that area, the big or the small area, then it doesn't change at all. And we find that our pressure, vapor pressure, is not dependent on size, but only dependent on temperature. The hotter it is, the higher the vapor pressure. And if we cool it down enough, we can lower the vapor pressure down quite a lot. In fact, for water, I'm going to give you a table here. You don't need to know this table or memorize this table, but let's look at the vapor pressure of water at various temperatures of water. We're going to start off at 20 degrees Celsius. Then at 20 degrees Celsius, the vapor pressure is 18 torr. Now, is that a big number or a small number? If you remember, there's 760 torr in 1 atmosphere. So the pressure around us is 760 torr, and we're talking 18 torr of pressure coming off of water at 20 degrees Celsius, which is about room temperature. That's not much. And that's our experience, right? Our experience is that water at room temperature does not evaporate all that quickly. And so that works out just fine. Now, if we cool it down, what do we think is going to happen? Well, we should find that less water comes off. And if we get our water down to 0 degrees Celsius, well, we're going to find that the vapor pressure is all the way down at 5 torr. Very, very slow. So even water at 0 degrees Celsius is still evaporating. Eventually, all of it will evaporate, but it's evaporating a lot slower. There's less gas coming off. Well, let's heat that up a little bit more. Let's get up to 90 degrees Celsius. What's the pressure there? It's 528 torr. Well, that's a big number. That's a lot closer to 760. We're getting close to an atmosphere of pressure. Well, when do we get to an atmosphere of pressure? We get to an atmosphere of pressure at 100 degrees Celsius. Well, that's an interesting number because if you recall, what temperature does water boil at? Well, it boils at 100 degrees Celsius. And so it turns out the boiling temperature here just happens to be when the vapor pressure is 760 torr, which happens to be 1 atmosphere. And the answer is no, it's not because it happens to be. That's actually the definition of something boiling. The definition of something boiling is the temperature at which the vapor pressure is equal to the atmospheric pressure. P vap is vapor pressure equals P ATM, which is the atmospheric pressure. And that gives us a neat thing. Well, does that mean if we change the atmospheric pressure that we change the boiling temperature? And the answer is yes. If you've ever read the instructions on pastaroni or things like that, occasionally they'll have high altitude instructions. And what do they mean by high altitude instructions? They usually tell you to cook it longer. Now, why would you need to cook things longer at high altitudes? And the answer is because at high altitudes, let's say you're up in the mountains and the pressure is only 528 torr. What's going to happen? You're going to have your little pot of water. It's got a little flame under it right there, warming it up. And when this water gets to 90 degrees Celsius, there's now 528 torr of pressure pushing up out of that water, 528 torr pushing down on it. And as you try to heat it up even more, what you're going to end up doing is boiling it and making bubbles. And your water is going to boil at 90 degrees Celsius. Now, if you remember, we talked about heating curves and cooling curves. What happens when something's boiling to its temperature? The temperature doesn't change. So once this thing starts boiling at 90 degrees Celsius, it doesn't get any warmer. So the reason there's these high altitude instructions on your box of pasta is because at high altitude, maybe you're only boiling the water and it's getting to 90 degrees Celsius, which just doesn't cook things as fast as it does at 100 degrees Celsius at sea level. So we can actually change the boiling temperature of water. In fact, we can change the boiling temperature of water to be down here at room temperature. You can boil water at room temperature. Now, you need special equipment to do that, either a syringe that you can tight seal really well, or what most people do is they use a vacuum system and they suck it out. If you really wanted to, you can search for YouTube videos on boiling water at room temperature. There's some really neat ones. And you can see they've got thermometers in there and they show you that this water boils at room temperature. It's pretty cool. So, boiling temperature is not a constant. Everybody thinks it's a constant. It's 100 degrees Celsius for water. No, it's 100 degrees Celsius for water at 1 atmosphere of pressure. But at 528 torr of pressure, it's 90 degrees Celsius. At 0 degrees Celsius, water boils when the pressure is 5 torr. The pressure in space is much less than 5 torr, so if you took ice water up into space, it would boil, which is pretty cool. All right, so that is our concept of vapor pressure. Any liquid, in fact, even most solids have a vapor pressure. They are constantly evaporating. Solids very, very, very slowly, liquids much quicker. And that vapor pressure is dependent on temperature. So here's a question for you to think about. Which of the following has the lowest vapor pressure? A teaspoon of water sitting on a counter, a large lake, a bottle of water with a small opening, or they all have the same? Hopefully you came up with they all have the same because we said, hey, vapor pressure doesn't depend on size. It depends on temperature. And since we didn't say, we had to kind of assume that all of these were at the same temperature. Now, what can we use this cool thing for? Well, it's kind of maybe a party trick or whatever to boil water at room temperature. But what about if you need to get water really hot? Well, we know from our heating curves for water that at 0 degrees Celsius, it melts. At 100 degrees Celsius, it boils. And once I get to 100 degrees Celsius, until it's all turned to a gas, I'm not going to get it any hotter. But what if I needed to get water hotter than that? And you might have heard of an autoclave before. It's a medical instrument for sterilizing things. And it turns out to really sterilize things, you need to get it to about 160 degrees Celsius, because that'll kill just about anything. Most things die in boiling water, but not everything does. Some things you have to get that higher temperature for. But if water only boils at 100 degrees Celsius and never any hotter, how can you get the temperature hotter so you can boil stuff and clean it? And that's where an autoclave comes in. And what an autoclave is it's actually just a fancy box that can get to really high pressures. Now, what kind of pressures? Well, let's talk about pressure and vapor pressure. Remember, at 100 degrees Celsius, the vapor pressure of water was 760 torr. At 120 degrees Celsius, the vapor pressure is 1,520 torr. Okay, so that is 2 atmospheres of pressure. So if I can make the pressure inside this 2 atmospheres, and I've got water down here, when it's 100 degrees Celsius, there's only 1 atmosphere of pressure pushing up and 2 atmospheres of pressure pushing down, and it's not going to boil. But when I get that water to 120 degrees Celsius, now there's 2 atmospheres pushing up, 1520 torr, 2 atmospheres pushing down, and as we try to heat it a little bit more, it ends up boiling. And so now we've got liquid water boiling at 120 degrees Celsius, which is really cool, but it's not quite 160. So it turns out an autoclave has to even get higher than that, and you have to get all the way up to 3,800 torr if you want to do that in an autoclave, and that is 160 degrees Celsius. Right, so that's how we use an autoclave. Now, this one over here is actually a good example because this is what we call a pressure cooker. If you've ever looked at or used a pressure cooker or seen, the chef shows where they use one, what does it do? It takes meat usually and cooks it really, really quickly. How does it do that? Well, it puts it in 120 degrees Celsius boiling water instead of 100 degrees Celsius boiling water. And it turns out there's a lot of proteins and stuff in tough meats especially that break down really rapidly at 120 that don't break down very rapidly at 100 degrees Celsius, and you can cook that meat a whole lot faster. So we can actually use it for useful things, either sterilizing stuff by getting up to 3,800 torr inside, or we can do a pressure cooker, and those generally run around 2 atmospheres of pressure. Molar volume, kind of a separate topic, not related to vapor pressure. How much volume does 1 mole of gas take up? And I'm not going to belabor the point. It turns out that it is 22.4 liters of gas is 1 mole of gas at conditions called STP. And what is STP? It stands for standard temperature and pressure. And what that means is 1.0 atmospheres of pressure and 0 degrees Celsius. Now, I don't know where standard temperature is 0 degrees Celsius, maybe way up in Alaska, but down here in Southern California, that is not standard temperature. But that's what we mean when chemists talk about standard temperature and pressure. They mean 0 degrees Celsius and 1 atmosphere of pressure. Now, it turns out that no matter what gas you have, nitrogen gas, 22.4 liters is 1 mole at STP. Hydrogen gas, yeah, 22.4 liters is 1 mole. How can it be the same? Hydrogen weighs like 2 grams, H2. Remember, it's a molecular diatomic. Nitrogen weighs 28 because it's a molecular diatomic, N2. How can something that weighs 2 grams per mole and something that weighs 28 grams per mole have exactly the same volume? It doesn't make a lot of sense. But it does, if you think about it. Hydrogen's moving really fast because it's very, very light at a given temperature. Nitrogen, being very heavy, is moving a little bit slower. So hydrogen is hitting the walls more often, right? And keeping up that 22.4 liters of space. Nitrogen is hitting it a little harder but less often, and also keeping up the 22.4 liters of space. So randomly, if I have 2.0 liters of gas at STP, what is the volume? And that's a very simple one. We're going to start with 2.0 liters of gas. We're going to try to determine the volume of gas. Liters is a good guess. Here's a hint. We only talk about STP once in this class. If you see STP or you see 0 degrees Celsius and 1 atmosphere of pressure, you probably are thinking about that 22.4 liters. What's got to go on top? Liters, so we get it over there. I'm sorry. Good one. I have 2 liters of gas. What's the volume? Oh no. How many moles? How many moles of gas? That's just funny. Right, so we actually don't want liters up there. We want moles down here. I thought that problem might be easier. I've got 2 liters of gas. How much volume my gas is? It's a nice problem. That would be nice to have on test. All right. Liters has to go on the bottom. Where does that come from? Moles and liters. Generally, if you see that, you're probably going to be using this number up here, 22.4 liters of gas. Numbers stay with their unit, so the 22.4 goes down there. We divide 2 liters divided by 22.4. What do I get? 2.0 liters divided by 22.4. I get 0.089 moles of gas. Okay, so 2 liters gas is only 0.089 moles of gas. 2 sig figs here, 2 sig figs here. This number does have 3 sig figs. It's not an exact number the way I wrote it. And so if you need to, you can use the 3 sig figs from that number. But here we were limited by the sig figs from the liters. You can also go the other way. And also commonly, some people do talk about grams of gas. They said, I've got 5.0 grams of nitrogen gas. And I wanted to know what's the volume at STP. Again, if you see that STP, that's a hint that you're going to be using the 22.4. But I can't go from grams of N2 straight to liters of N2 because I only have something that takes me from moles of N2. So what do I need to do? I need to do grams of N2 to moles of N2 to liters of N2 as my plan. So I'm going to start off with my 5.0 grams of N2. My first thing is to go to moles of N2. Grams got to go on the bottom, so it cancels out. Get my units first. I'm converting to liters of N2 over here. I need my moles of N2 to cancel out like that. Then we put in our numbers and our desired units here, liters of N2. So what kind of numbers do I get there? Liters of N2 and moles of N2 at STP. That's going to be 22.4 liters in 1 mole. Grams of N2 and moles of N2. You're like, what is that? That seemed like a while ago. Right? That's molar mass. N2, that is going to be 2 times 14.01 grams per mole is 28.02 grams per mole. And so where does that 28.02? Stays attached to its unit. Oops. If the screen doesn't move. 28.02 grams in 1 mole. So I'm going to multiply that out. I'm going to take 5.0. I'm going to divide by 28.02. Then I'm going to multiply by 22.4. And I get 3.997 liters. I've got 2 sig figs over here, so I only get 2 sig figs, and I get 4.0 liters of N2 as my answer. All right, so a balloon, a 4-liter balloon, which is a decent-sized balloon, only contains 5 grams of nitrogen. The air is mostly made up of nitrogen, so that balloon you have contains about 5 grams of gas. All right, one last topic for gases. After you solve a problem, we want to know what's the volume of 8.5 grams of sulfur dioxide gas. So go ahead and pause and try to figure that out. All right, hopefully you came up with something like this. Grams of sulfur dioxide, SO2. We're going to need grams of SO2 to moles of SO2 to liters of SO2. Now, I really should have specified at STP in this question, and on a test or quiz, I absolutely will. I'll either say at 1 atmosphere of pressure and 273 Kelvin, or I'll say at STP. And we do our first conversion, we do our second conversion, grams of SO2 on the bottom, moles of SO2 on the top, liters of SO2 on the top, moles of SO2 on the bottom. So we cancel those, we cancel those. Liters and moles, same as we had on the last slide. 22.4 liters in 1 mole. Here, SO2, what are we going to do? We're going to find the molar mass of SO2. It's 32 plus 32 is 64 grams in 1 mole. You can look that up yourself. So what do? I take 80.5, I divide by 64, I multiply by 22.4, and I get 2.975, or 3.0 liters from my 2 sig figs up here. So that's how we do grams to volume. Last subject in gases is what's called partial pressures. And what it basically says is this, is gases, they're so spaced, there's so much space inside a gas, that gases act independently. If I take a container and it's got 2 atmospheres of helium in it. I take a same container, it's got 4 atmospheres of argon. What I do is I take all the helium and I pump it in to the one that's argon. So now it's the exact same container. It contains both the helium and the argon. We want to know what's the pressure inside. Well, it turns out the pressure is just the sum of the pressure. So if this one was 2.0 atmospheres of helium, we had 4.0 atmospheres of argon, my total pressure is now 6.0 atmospheres, which makes a little sense, right? You add those gases together. But one thing we have to think about in here is, what's the pressure of helium in this container? Is it 6 atmospheres? Did we suddenly increase the pressure of helium by putting it into a container with something else? And it turns out the answer is no. Since there's so much space between gases, the helium basically acts as if the argon wasn't there most of the time. So the pressure of the helium inside the mixed container is the same as the pressure of the helium inside the container where only the helium was, or it's 2 atmospheres. And we call that 2 atmospheres the partial pressure of helium was 2.0 atmospheres in its empty container and also 2.0 atmospheres in the mixed container. And what you can do is you can mix as many gases as you want and they all act independently. One way to think about that is if you're weighing something. Right? If you're weighing some red grapes and they weigh 3.0 kilograms, and then you weigh some green grapes and they weigh 1.0 kilograms, the total mass is 4.0 kilograms, right? But it's not like all of a sudden the green grapes weigh 4 kilograms. Same thing for partial pressures. Just because you're adding those 2 gases together doesn't mean that they both behave as the sum of them. They still act independently. I still have 1 kilogram of green grapes, 3 kilograms of red grapes. The total's 4, but each acts independently. When I have gases, I can add their pressures to get the total pressure, but each still acts independently. And if I look just at the helium, it still acts like it has 2 atmospheres of pressure. And if I look just at the argon, it still acts like it has 4 atmospheres of pressure, even in that mixture. And that is the concept of partial pressures. We can sum up all the pressures of our gases to get the total pressure. And that's useful again in things like respiratory therapy, where you want to know maybe how much CO2 is, and you can measure O2 and know something about the nitrogen. You can figure out some of these total pressures and use partial pressure laws to get you there. Thanks for listening to this stuff about gases. We had, in this particular section, we talked about 3 main things. We talked about molar volume, partial pressure, and vapor pressure. And vapor pressure is what defines boiling, and we can see that boiling point change, which is one of the more interesting things that happens in gases. Thanks.